Known to the export market by the ambitious moniker Flying Leopard and to NATO observers as the more prosaic Flounder, the Xi'an JH-7A is not a machine of myth or legend. It is a quintessential product of unforgiving logic, a crucial if unglamorous stepping stone in China's long march toward aerospace autonomy. This aircraft is a case study in overcoming profound industrial shortfalls through focused design and sheer will, a story defined as much by its inherent limitations as by its formidable strengths. We are about to dissect this heavy-shouldered, purposeful machine from its core engineering to its strategic role. Subscribe to the channel so you don't miss new analytical reviews. The genesis of the aircraft lies in the strategic anxieties of the 1970s, a period when the People's Liberation Army Air Force, PLAF, and its naval counterpart, the PLANAF, were saddled with vast but increasingly obsolete fleets. Their primary strike assets, the Harbin H-5, a direct copy of the Soviet Ilyushin Il-28 Beagle from the late 1940s, and the Nanchang Q-5 Fantan, a 1960s-era ground attack aircraft derived from the MiG-19, were utterly outclassed by the platforms being fielded by regional and global adversaries. An urgent requirement was issued for a new, domestically produced aircraft capable of replacing these aging types. A modern, supersonic, all-weather fighter bomber that could penetrate defenses at low altitude and deliver a meaningful payload at long range. The program initially designated H-7 Hongjiaji, or Bomber, before being amended to the more accurate JH-7 Jianjiji Hongjiaji, or Fighter Bomber, was formally authorized by Deng Xiaoping on April 19, 1983. This was to be a monumental undertaking for the Xi'an Aircraft Industrial Corporation, XAC, and the 603rd Aircraft Design Institute, representing a steep and treacherous learning curve. It was, notably, China's first major combat aircraft to be developed using computer-aided design software, a technological leap that brought its own set of novel challenges and teething problems. At the heart of this challenge lay the most complex and persistent bottleneck in China's aerospace industry: the aero engine. Lacking a suitable indigenous high-performance turbofan, the designers at Xi'an had to look abroad. The solution they found was both pragmatic and revealing of the era's technological landscape. They selected the British Rolls-Royce SPA Menkei 202, a respectable but fundamentally 1960s-era low-bypass turbofan that had powered Western stalwarts like the F-4KM Phantom and the Blackburn Buccaneer. The plan was to import an initial batch and subsequently produce it under license as the Xi'an WS-9 Qinling. This single decision would fundamentally shape the aircraft's entire character, performance envelope, and ultimately, its strategic role. The first prototype, coded 081, made its maiden flight on December 14, 1988, an event that quickly descended into the kind of near disaster that gives test pilots premature gray hair. While returning to base, the newly installed engines began to vibrate with such catastrophic violence that, according to reports, 2/3 of the instruments were literally shaken from the instrument panel, and the connectors on the remaining third were rattled loose. The pilot, Huang Bingxin, managed to execute an emergency landing with little more than raw instinct and a prayer, a stark illustration of the fine line between ambitious engineering and a machine that requires a ritual dance just to stay in one piece. The aircraft would not dare to push past the sound barrier until nearly a year later, on November 17, 1989. The initial variant, the JH-7, which entered limited evaluation service with the PLANAF in the mid-1990s, was a deeply flawed machine. Plagued by technical problems, it was equipped with a rudimentary Type 232H radar, a three-piece windscreen that offered poor visibility, and a limited number of weapon hardpoints. The PLAF, assessing the aircraft's manifest shortcomings, flatly refused to procure it. This rejection, however, was not the end of the program, but the catalyst for its rebirth. The lessons learned from the troubled development and operational trials of the original flounder were channeled directly into a comprehensive redesign. The result was the JH-7A, an aircraft that, while visually similar to its predecessor, was in fact a vastly more capable and mature platform. It first took to the skies on July 1, 2002, and finally entered full-scale service with both the Plan F and the once skeptical PLAF in 2004. This entire development cycle, identifying a capability gap, importing a key foreign component as a stopgap, reverse engineering a domestic version, fielding an imperfect initial model to gain experience, and then leveraging that experience to produce a truly operational variant with upgraded indigenous systems, serves as a perfect microcosm of China's broader national industrial strategy. The JH-7A is not merely an aircraft. It is a physical manifestation of a national policy of import, digest, absorb, and re-innovate in action. In its final form, the JH-7A is a large and imposing aircraft, a testament to its intended role as a long-range strike platform. With an overall length of approximately 21 meters and a wingspan of 12.7 meters, it is roughly the size of an American F-4 Phantom. Its general configuration is dictated by its primary mission: low-level, high-speed attack. The high-mounted swept wings, featuring a noticeable 7-degree anhedral, are aerodynamically optimized for stability in the dense air close to the surface, providing a smooth ride during penetration runs. The fuselage is distinctly slab-sided and waisted at the wing junction, a design choice that bears a passing, if perhaps unflattering, resemblance to the European Panavia Tornado. The most significant structural evolution from the original JH-7 was the extensive incorporation of composite materials in the JH-7A's airframe. This shift from a conventional all-metal structure resulted in a lighter yet stronger airframe, a critical improvement that directly translated into enhanced performance. The weight savings allowed the maximum ordnance load to be increased from the JH-7's adequate 6,500 kg to a much more formidable 9,000 kg, transforming the aircraft's combat potential. This internal redesign was accompanied by several visible aerodynamic refinements that distinguished the A model. The somewhat crude wing fences of the original were deleted. The single large ventral fin beneath the tail was replaced by a pair of smaller twin ventral fins for improved directional stability, and the archaic three-piece windscreen was supplanted by a modern single-piece wraparound canopy that significantly improved the crew's field of view. At its core, the aircraft is powered by a pair of the aforementioned Xi'an WS-9 Qinling afterburning turbofans. Each of these license-built Spey-Menke 202 copies produces a static thrust of approximately 54.3 kN dry and up to 91.26 kN with afterburner engaged. An improved variant, the WS-9A, has also been developed, offering a modest thrust increase to around 97 kN. These engines propel an aircraft with an empty weight of around 14,500 kilos and a maximum takeoff weight of 28,475 keys. This power plant gives the JH-7A a respectable, if not world-beating, performance envelope. It can achieve a maximum speed of Mach 1.75 at high altitude and reach a service ceiling of around 16,000 meters. Its combat radius is a key metric, estimated at approximately 900 kilometers on internal fuel alone, but extending to a strategically significant 1,600–1,160 kilometers with external fuel tanks. The rate of climb at 190 mph is sufficient for its role, though it pales in comparison to dedicated air superiority fighters. The entire design philosophy of the JH-7A can be understood as a direct consequence of its engine limitations. China's well-documented struggles to master high-performance aero-engine technology forced the adoption of the Spey, a 1960s-era low-bypass design. Such engines are not optimized for the extreme demands of high-altitude, high-G air combat maneuvering. They are, however, relatively fuel-efficient and reliable at lower altitudes and subsonic speeds, the very regime where a strike aircraft spends most of its time. Consequently, the aircraft's physical form, its large, stable airframe, its high-mounted wings ideal for carrying heavy, drag-inducing ordnance, is not simply a strategic choice, but a brilliant engineering compromise. The JH-7A was meticulously designed to be the best possible strike aircraft given the engine it had, rather than being an idealized platform waiting for a hypothetical purpose-built engine. It is a fascinating and successful example of designing around a fundamental weakness to create a focused and effective strength. If the airframe and engines form the muscle and bone of the Flying Leopard, its avionics suite constitutes its digital nervous system, and it was here that the JH-7A represented a quantum leap over its predecessor. The cockpit was transformed from an analog relic into a modern glass workspace. While some traditional single-function dial indicators were retained as backups, the primary interface for the Tandem-Seated Pilot and Weapon Systems Officer, WSO, consisted of a head-up display, HUD, and two large color liquid crystal multifunction displays, MFDs. This arrangement, coupled with a domestically developed helmet-mounted sight, HMS, provided the crew with a level of situational awareness and data management that was state-of-the-art for Chinese industry at the time. Underpinning this was the introduction of a fully digitized quadruplex fly-by-wire flight control system. This was a critical upgrade, replacing direct mechanical linkages with electronic signals, which enhanced handling, improved stability, and, most importantly, allowed the aircraft to function as a rock-steady platform for precise weapons delivery, especially during turbulent low-altitude flight. The single most important upgrade, however, was the replacement of the primitive Type 232H radar of the original JH-7 with the JL-10A Shan Ying Mountain Eagle. This indigenously developed J-band pulse Doppler fire control radar system elevated the aircraft into the modern era. The JL-10A possesses a maximum detection range against aerial targets of approximately 104 kilometers, with a lookup tracking range of 80 kilometers and a crucial look-down tracking range of 54 kilometers, allowing it to distinguish targets from ground clutter. Built to the MIL-STD 1553B data bus standard, it is compatible with a wide range of systems and can reportedly track up to 15 targets while engaging up to 6 of them simultaneously. With 11 modes of operation, including ground mapping, Doppler beam sharpening, and a terrain-following capability, the JL-10A provides the JH-7A with a genuine all-weather, day-night, look-down, shoot-down capability and is the key enabler for its diverse arsenal of precision-guided munitions. This offensive capability is protected by a comprehensive defensive electronic warfare suite. Internally, the aircraft is equipped with a radar warning receiver, RWR, chaff and flare dispensers located at the base of the tail fin, and a BM-KJ-8605 noise jammer. However, the true potency of its electronic warfare capability lies in the external pods it frequently carries. The JH-7A is often seen equipped with powerful KG-600 or the newer KG-800 jamming pods, as well as pods designed for electronic intelligence, ELINT gathering. This ability to carry sophisticated electronic warfare equipment suggests a doctrinal employment that goes beyond simple self-defense. It points to the use of the JH-7A not just as a kinetic shooter, but also as a dedicated electronic attack platform. A typical strike package might consist of several aircraft, with some configured as missile carriers and others tasked with suppressing enemy air defenses, using their powerful jamming pods and anti-radiation missiles to blind and neutralize enemy warship radars like the American Aegis system. This transforms the JH-7A from a mere missile truck into an integrated and sophisticated component of a suppression of enemy air defenses (SEAD) campaign, dramatically increasing the survivability and combat effectiveness of the entire formation. The JH-7A's raison d'etre is to carry a heavy and diverse load of ordnance to a distant target. Its airframe is studded with 9 hardpoints, 6 under the wings, 2 at the wingtips for self-defense missiles, and 1 on the center line, capable of carrying a total of 9,000 kilos of weapons and external fuel. Its arsenal is tailored for its primary missions, chief among them being maritime strike. For this role, the aircraft can carry up to 4 formidable anti-ship cruise missiles. The standard loadout includes subsonic sea skimmers like the YJ-83K with a range in excess of 180 kilometers, or the air-launched KD-88, a versatile missile with an imaging seeker. The platform's threat potential is set to increase dramatically with the planned integration of the YJ-12, a large supersonic anti-ship missile capable of speeds approaching Mach 4 and ranges of up to 400 kilometers. A salvo of such weapons would pose an extreme challenge to even the most advanced naval air defense systems. For land attack missions, the JH-7A's capabilities are equally comprehensive. It can deploy a wide array of precision-guided munitions, a capability enabled by its JL-10A radar, and the carriage of an external KADC-03A targeting pod. Its inventory includes laser-guided bombs such as the 500 kilo LS-500J and satellite-guided bombs from the LS-6 and FT families. For targets requiring a greater standoff range, it can launch missiles like the television-guided Russian KH-29T or the domestic KD-88 air-to-surface missile. This precision strike capability is complemented by a potent SEAD, suppression destruction of enemy air defenses, role. To hunt and destroy enemy radars, the JH-7A employs anti-radiation missiles like the LD-10 and the YJ-91, a Chinese derivative of the powerful Russian KH-31P. While emphatically not designed as a dogfighter, the aircraft is far from defenseless in the air-to-air arena. Its wingtip pylons are dedicated to carrying short-range, all-aspect infrared-guided missiles for self-protection. These typically include the reliable PL-5C, a weapon in the class of the AM-9 Sidewinder, and the more capable PL-8, a license-built version of the highly agile Israeli Python 3. Cued by the pilot's helmet-mounted sight, these missiles provide a respectable defensive capability against intercepting fighters. For close-in engagements, the aircraft is fitted with an internal twin-barrel Type 23-3 23mm cannon, a copy of the Soviet GSH-23L, supplied with 200 to 300 rounds of ammunition. With approximately 240 units in service, split almost evenly between the PLAF and PLANAF, the JH-7A is a mature and widely deployed asset in China's armed forces. It is a frequent participant in military exercises and a common feature in patrols conducted in the contested airspace of the South China Sea and around Taiwan. The platform has also gained significant international exposure, most notably through its consistent participation in the Falcon Strike series of joint exercises with the Royal Thai Air Force. In these complex drills, JH-7As have operated as part of integrated packages alongside more advanced J-10C fighters and KJ-500 Airborne Early Warning and Control AEW&C aircraft, training in realistic scenarios against Western-designed Saab Gripen fighters. These exercises have focused on air support, ground assault, and joint force operations, providing invaluable experience for PLA pilots and commanders. Recent domestic exercises have also highlighted the JH-7A's growing versatility, particularly in the Close Air Support (CAS) role. With the retirement of China's only dedicated attack aircraft, the rugged Nanchung Q-5, the JH-7A has been tasked with providing direct fire support to ground forces, a mission for which its large payload and stable flight characteristics are well suited. However, the aircraft's most critical strategic function is its role as a linchpin in China's formidable anti-access area denial A2AD strategy. The entire concept of A2AD is to create a layered defensive bubble that can hold an adversary's military forces, particularly a U.S. Navy carrier strike group, at risk, thereby deterring or defeating third-party intervention in a regional conflict. The JH-7A, with its long combat radius and heavy payload of anti-ship missiles, is a key kinetic element of this strategy. Operating under the guidance of AEW&C aircraft and leveraging its own potent electronic warfare capabilities, it forms a credible and lethal layer within this defensive system. The aircraft's participation in complex cross-service drills is about more than just honing pilot skills. It is about stress testing the command, control, communications, and intelligence networks that bind the entire A2AD system together. When a KJ-500 guides a flight of JH-7As toward a distant naval target, or when a ground-based Special Forces team provides coordinates for a SAS mission, the PLA is practicing the very kind of joint force integration that was historically its greatest operational weakness. In this sense, the JH-7A serves as a relatively low-cost, high-volume platform used to mature the PLA's nascent joint operations doctrine. It acts as a set of training wheels, providing the invaluable lessons in networked warfare that will be directly applied to the operation of more advanced platforms like the Shenyang J-16 and Chengdu J-20. To truly understand the JH-7A's place in the pantheon of military aviation, it must be compared against its genuine peers. A common analytical error is to place it in the same category as the American F-15E Strike Eagle or the Russian Su-34 fullback. The F-15E is a true multi-role strike fighter derived from one of the most successful air superiority fighters ever built. It possesses vastly superior engines, flight performance, radar, and air-to-air capabilities, making it a dominant fighter that also happens to be a superb strike platform. The Su-34, with its unique side-by-side armored cockpit and enormous fuel load, is a dedicated long-range bomber designed to replace strategic assets like the Tu-22, operating in a class of its own for deep penetration missions. The JH-7A, with its 1960s-era engine architecture and specialized design, cannot realistically compete with either of these heavier, more advanced, and far more expensive aircraft in terms of multi-role flexibility or kinematic performance. The most accurate and insightful analog for the CN-JH-7A is the Panavia Tornado IDS. Both were developed in the 1970s and 1980s with a shared design philosophy: to create a two-seat, twin-engine strike aircraft optimized for low-level, all-weather penetration missions. Both platforms prioritized payload, range, and a stable ride in dense, low-altitude air over high-G air combat agility. The Tornado's primary advantage lies in its variable sweep wing design, which provides superior performance across a wider flight envelope, particularly in low-level ride quality and short-field takeoff and landing. The JH-7A, on the other hand, boasts a slightly higher maximum payload capacity and, in its current iteration, arguably a more modern and cohesively integrated indigenous avionics suite than the Tornado IDS variants it replaced. Furthermore, the JH-7A's primary armament of long-range anti-ship missiles is more central to its core design purpose than the Tornado's more general-purpose ground attack role. In essence, both aircraft represent parallel solutions to a similar set of tactical problems, shaped by the distinct technological capabilities and strategic priorities of their respective developers. The Xi'an JH-7A Flying Leopard is now in the long twilight of its service life. It continues to receive incremental upgrades, such as the JH-7A variant seen in 2019, which is believed to feature improved radar processing for better integration with newer jamming pods and munitions. A more ambitious JH-7B, which was rumored to incorporate stealth features, an in-flight refueling probe, and more powerful WS-9A engines, appears to have been abandoned, as its intended role is now being filled by a far more capable successor. That successor is the Shenyang J-16, a Chinese multi-role strike fighter derived from the Russian Su-30 MKK, which combines the payload and range of a dedicated strike aircraft with the high performance and agility of a heavy fighter. As J-16 production ramps up, the JH-7A fleet will inevitably be drawn down, its frontline duties passed to a new generation. Looking further ahead, a new, stealthy three-engine fighter bomber is reportedly in development, destined to eventually replace the JH-7 and J-16 fleets entirely. In the final analysis, the JH-7A will not be remembered as a legendary fighter or a revolutionary design. It will be remembered as a vital and dependable workhorse. It was the aircraft that allowed China's aerospace industry to bridge a critical technological and doctrinal gap, providing the PLA with a credible, long-range maritime strike capability at a time when no other domestic option existed. It served as an invaluable test bed for maturing key technologies like fly-by-wire controls, pulse Doppler radar, and precision-guided munitions. Most importantly, it was the platform upon which the PLA learned the complex art of modern joint force operations. The legacy of the Flounder is that of a pragmatic, imperfect, but ultimately successful tool that did its job, paving the way for the far more formidable Chinese combat aircraft that now follow in its wake. The JH-7A was never intended to be the crown jewel of Chinese air power, and that reality is fundamental to understanding its purpose. Unlike the Chengdu J-10 or the stealthy J-20, which are tasked with winning air superiority, the Flying Leopard was conceived from the outset as a pressure tool, a strike platform designed to impose cost and risk on adversary naval forces and critical infrastructure. Within China's broader anti-access area denial framework, the JH-7A represents a crucial mid-layer of deterrence. Coastal missile batteries and submarines provide the initial hard crust, but it is the Flying Leopard, armed with long-range anti-ship missiles, that delivers massed, flexible strike capability from the air. This philosophy echoes Soviet concepts of maritime aviation, where land-based bombers and strike aircraft were tasked with saturating carrier groups and cutting off sea lanes. Yet China adapted and expanded the model. The JH-7A is not confined to a maritime strike role. It has demonstrated equal utility in deep interdiction against airfields, logistics nodes, and surface-to-air missile sites. Particularly telling is its utility in suppression and destruction of enemy air defenses. Exercises consistently feature JH-7As carrying electronic warfare pods and anti-radiation missiles, deliberately configured to burn holes through adversary radar coverage. In this role, the Leopard is a force enabler, creating corridors for more advanced multi-role fighters like the J-16 and stealth penetrators like the J-20. Seen in isolation, the JH-7A can appear an anachronism, a large twin-engine strike aircraft powered by engines rooted in 1960s technology. But its real value lies not only in operational service, but in what it taught the Chinese aerospace industry. This was China's first combat aircraft designed with computer-aided design software, its first significant application of composites in a frontline airframe, and one of its earliest platforms to incorporate a digitized fly-by-wire system. Each of these milestones represented both risk and reward, and each became a foundation for future aircraft. The avionics revolution it brought forward, transitioning from a largely analog cockpit to a glass interface, integrating multi-function displays, helmet-mounted sights, and digital data buses, provided the industrial base and the pilot corps with the experience necessary to handle far more complex platforms later on. Likewise, the JL-10A radar and electronic warfare integration demonstrated that China could not only field but also iteratively refine indigenous sensor suites in line with international standards. Perhaps most importantly, the Leopard embodied the national policy mantra of import, digest, absorb, and re-innovate. The Rolls-Royce SPA engine was not an ideal solution, but it gave Xi'an Aircraft Industrial Corporation a starting point from which to build the WS-9 and its subsequent derivatives. The experience of fielding a flawed but serviceable aircraft, then redesigning it into the more mature JH-7A, became the living example of China's crawl, walk, run strategy in aerospace development. As of today, the Flying Leopard remains operational in both the PLAF and PLANAF, with roughly 240 units still serving. Incremental upgrades such as the rumored JH-7AI with enhanced radar processing and electronic warfare compatibility extend its relevance, but its trajectory is clear. It is a transitional machine, bridging the technological gap between 20th century Soviet derivatives and 21st century indigenous multi-role fighters. Its successor, the Shenyang J-16, represents the destination toward which the Leopard pointed, a heavy, agile multi-role fighter bomber combining payload, range, and kinematics in a way the JH-7A never could. And beyond the J-16 lies the future. Stealth-oriented designs, possibly even the rumored stealthy tri-engine strike bomber under development. The JH-7A will fade into twilight not with the glory of a legend, but with the satisfaction of a workhorse that did precisely what it was intended to do: hold the line, teach the lessons, and prepare the ground for what comes next.